So yeah, welcome to my talk, Get Ready to Rustle. If you're wondering what that's supposed to mean, I have no answers for you really. I just chose it because I was looking for something that included the term Rust in some way, and then the idea was to use it as a working title and fix it later, but like everybody knows what fixing something later means, right? So here we are with this strange title, but I think, or I hope the talk is going to make more sense to you than the title. My name is Marco Otte-Witte. I'm founder of maintainability. We are a web development consultancy. We do sort of custom development. We advise and mentor teams that do development themselves, and then we help them sort of overcome obstacles, adopt new technologies, and ship better results faster and more reliably. And last year, we made a strategic bet, as we call it, on Rust, because we think it's great, right? And we think the clients that we work with can benefit greatly from it. And our goal is to help those teams sort of to adopt Rust and take advantage of its benefits, right? Which they might not feel comfortable sort of taking on their own. And to share our excitement for Rust, we also created a conference around it, which is called Eurorust. The second edition just happened 2 weeks ago in Brussels. It was a pretty big success. I think that's fair to say. Obviously, I'm biased, but that's the feedback that we got from attendees. Yeah, so this year's edition just ended, but you can save the date for next year already. The host city is going to be announced, but it's hybrid conference, so you can also attend remotely. And we're not the only ones who are excited about Rust, right? Rust was voted the most admired language in the 2023 Stack Overflow survey, and so it was in 2022, and in 2021, and 2019, 18, 17, 16, right? So really, Rust is drowning in sort of developers' love, and it has been for a while, right? And the Stack Overflow users aren't even the only ones who love Rust. The decision makers at the big corporates, right, love Rust no less, really. All of the big players in the industry, right, are in the process of adopting Rust in quite significant ways, right? AWS uses it heavily for their platform. Google uses it in Android. Microsoft is using it in Windows. It's used in the Linux kernel, and it flies planes and satellites already, right? So essentially, Rust is replacing C and C++ everywhere those languages were used before, really, right? Which is systems programming, operating systems, all kinds of embedded systems, low-level tooling, as well as games and game engines. I want to look at a slightly different area today, though, which is the web, right? And specifically backend web development. And that's not necessarily an area, of course, where anyone used C or C++ before, right? Unless maybe some very strange edge cases. So Rust is not really an obvious choice there, right? Because you're not replacing C and C++. Yet we think Rust has a lot of potential in that area, actually, as it gives teams sort of building web and cloud apps access to capabilities that were previously out of reach for them, right? And what those are, we'll see in more details later. And while the web and cloud space is a young and sort of evolving area for us still, there are quite a few companies that already use Rust in that area, and quite successfully so. So in this talk, I want to talk about the what, the why, the how and where of Rust for backend web development, and then finally look at where Rust on the web is going. So let's start with the what, right? What am I even talking about here with Rust? So welcome to my 5-minute intro to Rust, although my team told me when I practiced this, it's actually a bit longer than 5 minutes, but it's going to be fine. So Rust's tagline is a language empowering everyone to build reliable and efficient software. And the word empowering really is central here, right? Like Rust empowers large parts of the industry to achieve reliability and efficiency at levels that were previously completely out of reach. So let's see what the language looks like and sort of how it keeps that promise. First of all, some bad news. 4 spaces for indentation is the default in Rust. I, like everybody else here, I guess, know that 2 spaces is actually the correct number, but this is sort of a bitter pill we have to swallow when working with Rust. Everything else is great, right? So let's start with the basics. Rust is strongly and statically typed, right? You either type things. Is that fine? If it happens every now and then? I guess it's not too interrupting. So you can either type things explicitly or let Rust infer types, where it can, really. Unlike in many other languages, variables are immutable by default, right? So trying to change a variable after it has been assigned a value, like in this example, results in a compile error. And by the way, as you can see, Rust has pretty good error messages, right? They're typically well written and almost always sort of suggest a way to fix the error that will also actually work. So while variables are immutable by default, there's opt-in mutability as well, right? This example comes fine since X is sort of explicitly marked as immutable. Also, unlike many other languages, there is no concept of implicit nullability in Rust, right? Which exists in most other languages, where sort of any reference can typically also be null, and you need to check for that to be sure. The only similar concept in Rust is the unit type that's expressed as an empty pair of parentheses here, and that represents the absence of a value, right? Since the unit type is an actual type, though, assigning it to a variable that's of a different type fails at compile time, right? And that's different from languages like Java and others, where any reference type could also always implicitly be null, and you only know for sure at runtime when you get a null pointer exception or not, right? And in Rust, that cannot happen, as the type checker prevents it at compile time, which obviously is very variable. Next, let's look at built-in types. Like besides regular number, floating point, character, and so on times, Rust also has a number of compound types. There is tuples that represent collections of values of different types. There is fixed length arrays and also other sort of collection types, obviously. There is structs for representing structured data, and Rust supports generic data types as well. Besides these, Rust also has enumerations that can also hold data, right? Like in this example, the key press variant of the event enum holds the key code of the key that was pressed, right, as a data element. And these enums are used for 2 types in the Rust standard library that are used pretty extensively in the Rust world, and thus are worth mentioning here. One is the result enum, which is used for operations that can fail, right? Rust does not have exceptions, so you typically use the result enum to indicate if things went wrong. And result has 2 variants, OK and err, and is generic of the types of the values associated with these variants, right? In this example, we have a try function that returns a result, and we're using a U16 number for the OK case and a custom error struct for the error case. And when calling the function, we can use Rust match statement to handle the 2 possible cases, right? The case where things work fine and we receive the U16 as well as the error case. A bit similar to the result enum is the option enum, which is used to represent the presence or absence of a value. And this is roughly similar to the implicit nullability in languages like Java, maybe, just as like explicit in this case and more expressive, really, right? The option enum has 2 variants, sum and none, and is generic of the type of the value that's associated with a sum variant. Show me touching the cable, maybe. In this example here, the getValue function returns an option of U16, right? And when we call the function, we can use a match statement again to handle the 2 cases, right? Either we get sum, U16, or we get none. So now that we've seen the basic language features and types, I'd like to address the elephant in the room, and I'm sure most of you have heard already about Rust's ownership system. Right? It's a bit of a complex topic, and everybody who comes to Rust fresh is scared of it, and I have to admit that it's at least partly justified. So let's go over what it is. So first of all, Rust is not doing garbage collection, right, for memory management, like Java, for example. And it also doesn't require developers to manage memory themselves, like C or C++ do. Instead, it does compile-time memory management, essentially, right? And to enable that, for every value, Rust tracks ownership as the variable that owns the value, right? And when the scope, the variable, was defined in ends, Rust knows it's safe to release the variable from memory, since the variable went out of scope and sort of the value doesn't have an owner anymore and can't be accessed anymore anyway. And then compile time, sort of Rust can sort of automatically inject all of the memory management for you, right? Because it can see sort of where to release things. And we don't go too deep into this topic because it would kind of be a talk of its own, and this is supposed to be the 5-minute intro to Rust. But here's a brief example to illustrate the gist of it. So the variable Ferris here holds a string and is defined in the scope of the main function, right? So the Ferris variable is the owner of that string value. We then pass the value into the uppercase function, and by passing the value the Ferris variable owns into the uppercase functions, the ownership of the value changes, and the name variable or argument of the function becomes the new owner of that value. And Rust knows that at the end of the scope of the uppercase function, when the name variable goes out of scope, the value it points to can be freed, as the value's owner is now out of scope and cannot be accessed anymore. Yet in the main function, we're accessing the value via the Ferris variable in the print line statement that runs after the uppercase function has returned and the string value has been released. Right? And that can't work, and we get a compiler error. And this slide might seem a bit much, but sort of once you get the basic idea, all of this text makes sense. Right? In this case, a simple fix for the error would be, instead of passing the value and thus passing ownership, we could pass a read-only reference so that ownership stays with the Ferris variable. Right? And the uppercase function simply borrows the value. You might have heard about of borrowing in the context of Rust. And this example will compile fine, right? As ownership remains with the Ferris variable, which is defined until the end of the scope of the main function, so that the string value only gets freed after the print line statement. As I said, this is a bit of a complex topic, so just know Rust doesn't do garbage collection and also doesn't require developers to manage memory manually. Instead, it has that ownership system which allows it to do compile-time memory management. So that's the brief overview of the language itself, but I wanted to talk about using Rust to build web backends, of course. So what's the situation with Rust on the web, right? Is Rust web yet? And are we web yet.org answers the question with a clear yes, right? Rust is ready for the web, and it's also freaking fast. All of the different things you need to be covered in order to be able to write web apps are covered in the Rust ecosystem. First of all, there is Tokyo, which is an asynchronous runtime, and it's sort of the foundation for most of the web frameworks and similar libraries. It's kind of the main building block for Rust on the web. On top of that, there are web frameworks. There are quite a few mature, well-maintained options there, with Exum being the most popular one, building on top of the Tokyo runtime. And without going into details here, I just want to say sort of that all of the lower-level stuff you need when writing web backends like HTTP 123, WebSockets, TLS, and so on is essentially covered by these frameworks. And then sort of below the web frameworks, you have the data stores, right? And sort of mature and well-maintained drivers exist for all of the relevant data stores as well. There's ORMs as well, if you want to use one. And there's even a number of data stores that are written in Rust themselves, right? As obviously Rust is a great choice for that kind of software. And then there's a number of other things you need when writing web apps, right? Like serialization, deserialization, which is covered by the famous, like in the Rust world, famous Sorbet crate. There's implementations of varying messaging formats. There's crates for internationalization, as well as templating, and essentially everything else you'll need, right? So overall, as awewebbear.org said, yes, Rust is ready for the web, right? And as I said in the beginning, we at mainmatter believe that building web apps with Rust is ready for takeoff, right? And it will take off in the near future. And it's also relatively easy even, right? And to illustrate that, I want to start with a small Express.js app, right? Obviously, we could have used other things like Sinatra, Python, Ruby, or Go stuff or whatever, but we chose Express here. And in this example, we are running a server on port 3000. And then we respond to GET requests to the root path with a static string, right? It's pretty straightforward. And the equivalent in Rust is actually pretty similar, right? We import some types here. We find a main function, which we mark with Tokyo's main attribute macro to allow it to execute asynchronously. And then we create an application and route GET request to the root path to a hello world function. Right? And the rest of the code of the main function essentially just starts up the server and binds it to port 3000 on localhost. And the hello world function itself simply returns a static string, like in the Express example. So that concludes the intro to Rust and the state of web development in Rust, right? But you might ask now, why? Right? Why should you care when you're happily using Ruby or Java, Elixir, TypeScript, or Go, or whatever you're using to build your backends? And to explain why you might decide for Rust in some scenarios, let's go back to our previous example. Seemingly, there isn't a big difference between the two, just looking at the code, right? Like one implementation is typed, and the other is not, and Rust has a bit more sort of ceremony, and this gets a bit longer, but overall it's actually quite similar. However, when running these examples, we see there's actually a huge difference, right? For a simple load test, we managed to complete around 13,000 requests in 10 seconds for the Express server, right? On this notebook, I think I ran that. With the same load test, in the same time, we managed almost 130,000 requests against the Rust server, so that's roughly 10 times the request for the Rust server versus the Node server. So you might all have heard already, and it might not really be a surprise, that Rust is just extremely fast, of course, right? But it's not just much faster on average. Performance is also much more consistent, right? The problem with all garbage-collected languages, like in this case JavaScript, is that performance charts look something like this, right? There are spikes, sort of, which occur in intervals, where performance is much worse than the rest of the time, right? And of course, those spikes occur when garbage collection runs, right? And the VM holds everything else to be able to clean up unused memory. For a language like Rust that does not have garbage collection, the performance chart looks like this, right? It's a flat line without peaks. You sort of get consistent performance all of the time, right? For 100% of the incoming requests. And before Rust came along, sort of the only languages that allowed to get this kind of high and consistent performance were C and C++, right? And maybe some other sort of more exotic languages. The problem with C and C++, though, is that using them is like juggling chainsaws, right? And this is not something that I say, but something that Linus Torvalds says. And he must know, right? He must have written like hundreds of millions of lines of code in these languages. So C and C++ are obviously very powerful, but also really dangerous, right? There's a lot of pitfalls, like most prominently making mistakes, doing manual memory management, which can have horrible consequences for security and stability of your service as well, of course, right? So you can really only dare to use C and C++ when you're an expert or sort of you have an expert team, right? Which essentially nobody has in the web and cloud space, right? Where everybody is using very different languages like JavaScript or Ruby or whatever. And that means sort of that a certain level of performance and inefficiency sort of has been out of reach for these teams, right? Until Rust came along and sort of enabled everyone essentially to reach those previously unreachable levels of performance and efficiency while protecting people from hurting themselves, right? Via the ownership system and relating mechanisms sort of that allow Rust to do compile-time memory management. And the performance and efficiency of Rust aren't only relevant so web servers can deliver responses faster, right? Like having a server that only needs 1/10 of the time to respond to a request also means, obviously, so we can respond to the same number of requests with 1/10 of the servers, right? Admittedly, this is a bit of an oversimplification, but I think you get the point, right? And being able to say and being able to serve the same number of requests with 1/10 of the servers also means that we only spend 1/10 of the hosting cost, of course, right? And that can actually make quite a substantial difference in some cases, right? Cloud hosting is great in many ways, but it's certainly not cheap, right? There's also this movement sort of moving away from the cloud going on right now for similar reasons, right? But it's still like, even if you self-host, you don't want to waste servers necessarily, right? But in particular, when you're hosting on the cloud, sort of being able to switch off 90% of your servers can easily result in sort of saving hundreds of thousands of euros or whatever, even for not super huge companies. And these savings with Rust are real, right? This is a bit of a random quote from Reddit, which admittedly is not really a scientific source, but sort of the numbers they mention are representative, right? Like this person is saying they can fit 4 Rust services on a node that fit 1 Python service before, and each of the Rust services achieves 14 times the throughput of their Python services, right? So they can switch off and stop paying for a bunch of servers because of Rust, right? And switching of servers doesn't only save money, right? But of course, only using 1/10 of the servers compared to before also means we're only using 1/10 of the energy, right? And I think that's something we should all care about as well, since running data centers on renewables and so on is good, but the greenest energy is the energy we don't use, right? And then maybe we can use the renewables for something else. It would be obviously ridiculous to claim that Rust is going to solve climate crisis or so, right? But I believe it's important to understand and acknowledge that the software that we write sort of uses real resources in the end, even we don't see that really from our notebooks. And thus what we do has an impact on the real world, obviously, right? And if we can use sort of resources more efficiently and get the same or even more output for less input, that's good, right? So the performance and efficiency that Rust comes with is one good reason, I think, to care about Rust also on the web, right? But there's another reason that's maybe not as obvious and therefore typically overlooked a bit when talking about Rust, and that's the reliability and maintainability improvements that you get through Rust's powerful type system. And to illustrate that, let's look at some typical code from a web app project. And in this case, this is Ruby on Rails, if you're not familiar. It's a pretty neat piece of code, really, right? And it's expressive, and sort of writing code like this, sort of you can reach your goal fast, right? However, there's some problems as well, right? We can see the user's attributes, but there are no clear rules there regarding sort of what values are allowed in what combination, or sort of can be expected to be set or not set in particular scenarios, for example, right? So if the active attribute is true, then activation date must probably be set as well, right? If active is false, we assume activation date must not be set because it wouldn't really make sense, right? We can look at the activate methods implementation sort of to validate those assumptions, but these things are not encoded in types or interfaces or sort of clear rules anyway. And the signature of the activate method also doesn't tell us what the argument is exactly, right? Whether it's a date or a timestamp, if it's a time, what time zone. And looking at the usage of the method, sort of, we don't know whether the invocation potentially throws an error, right? And while Ruby is a bit of an extreme example, maybe, many of these problems can be found in other languages as well, for example in Java, right? Where we would also have no way sort of to express those rules around the active and activation date attributes and sort of allowed versus not allowed combination sort of in types or so, where things can be null, right? And we can get null, where things can be null and we get null pointer exemptions at runtime as we discussed before, and where we can see a development time whether a method we're calling might throw an exception, right? And nothing forces us to handle all possible exceptions, right? So they end up being thrown without being handled in runtime. And then they take down our services in the worst case. These problems all might seem a bit made up and not too relevant in reality, maybe you also don't want to sort of let go of your freedom and ability sort of to freely express yourself without constraints when programming in flexible languages like this, right? Like DH8, right? The creator of Rails seems to consider types a chore that sort of take the joy out of programming somehow, right? And I admit I can relate to this sentiment in a way, even. But the problem in reality is that sort of the longer you work on your app and the larger the code base becomes and the larger the team working on it becomes, sort of the more you start to feel the impact and the pain that those problems mentioned before are causing, right? You don't have a small, tightly knit team anymore, right, where everyone understands sort of the entire code base and is aware of all of those concepts and rules that are somehow present in the code, but only kind of implicitly. So in order to be able to reason about the code base and to know whether a change here might break something over there, right, you need to read through classes and methods and tests, and you have to rely on really good test coverage and so on, right? And you get relatively little help from the language itself or the tooling. And sort of the bigger the and the bigger the code base becomes, sort of the more unrealistic that task becomes of sort of reading through everything and figuring out all of the spaces sort of that might be affected by a change you make. And the harder it becomes also in particular for new joiners to work with the code base, right? And typically also your error rates goes up as sort of people make mistakes, right? Because they are not aware of all of the implicit rules there. So there's immense value with regards to reliability and maintainability in having types and having a rich and expressive type system, right? Which, by the way, of course, is also the reason for things like TypeScript and like types in Ruby and Python and all of the other languages, right? Like people start to feel the pain and then they come up with solutions. So looking at the same piece of code as before in Rust, right? First of all, for the user model, we can use an enum, right, with associated data as I showed before, right? Like this way, it's completely clear what inactive and active users look like, right? Inactive users don't even have the same attributes as active users. So there's no question what should or should not be said in what combination, right? And for the activation date, we even have the time zone we expect right in the type. So we're clearly communicating sort of those rules that were all implicit in the Rails example here, right? And because of that, this code is much easier to reason about and much more approachable for a newcomer to the code base. Plus, the compiler will enforce the rules, so there's only very little room for making mistakes here, right? And then for the activate method, we know exactly what the argument is as it's typed, right? Again, even the time zone is in the type here. And we also know the activation date will always have a value because, as we saw before, there's no concept of implicit nullability in Rust, right? If the activation date could potentially not have a value at the place where we retrieve it, it would be an option enum probably, right, as we saw before, and the compiler would require us to handle both the some and the none cases and only allow this activation function to be called if there was some value sort of for the some code path for the activation date, right? And the function signature also makes it clear there can be a database error here when calling it, since it returns Rust result enum, right? And when calling the function, we have to handle both of the cases, right? Like both the success and the error case. And there can be no unhandled runtime exception that sort of in the worst case takes down our entire service then, as simply it would not compile if one of the cases will not be handled. Obviously, this is a rather simple example, but I think it illustrates the point, right? Like this Rust code is clearly more expressive, more maintainable, and more reliable than the previous Rails code snippet, right? And it also goes far beyond other typed languages like Java or Go as well. So these improvements in reliability and maintainability are what I believe the second reason why you would want to consider Rust, right? Maybe the reason that's more relevant than the performance and efficiency gains in many cases. So now, having the what and the why established, let's look at how and where to adopt Rust on the web. I want to talk about some typical use cases and adoption path. So first of all, we've already established that Rust gives you reliability, maintainability, efficiency, and performance. Right? So use cases for us are obviously cases where those four things are relevant. And then, of course, you could say those are always relevant, and you'd be right, but you also don't really get these benefits for free, right? There's a cost associated with using Rust. If you compare Rust to alternative technologies, so if you clearly get more value out of Rust compared to any of the alternatives here, right? You get better performance and efficiency and more stable performance, as we've seen, because there's no garbage collection, and you get better reliability and maintainability as well. All that value does come at a cost though, right? You will initially invest more effort into building a system with Rust than you will with Go, and even more so compared to JavaScript or Ruby that are kind of made for getting results fast, right? So compared to those, Rust obviously doesn't leave you as much freedom, and sort of you need to make sure your program passes all of the compiler's checks before you get a working result, right? Plus, there's a few mountains you need to climb before you're productive with Rust. For example, we talked about the ownership system, which takes many people some time to learn, right? However, when you look at mid and long-term productivity of teams working on Rust code bases, things look quite different, right? Like while the initial effort is high, sort of, and getting up to a good level of productivity takes a bit, you'll see that over time, teams will be able to reach high levels of productivity, and they will be able to stay on that level then, right? As Rust code is easier to reason about, and the compiler will catch most mistakes, so if you can more confidently make changes, right? Even on large code bases with large and growing teams. And because the compiler catches so many bugs and your code is more reliable, you'll also be spending less time fixing bugs. And that tends to look pretty different for other languages, where you get to work in prototypes super fast, but then when the problems sort of show over time and get worse and worse and worse and worse and worse, and with that, sort of your productivity goes down. I have seen some teams with like old and big Rails code bases, for example, right? They were like almost completely paralyzed and unable to make any meaningful progress at all, since nobody could reason about the code base anymore, right? And foresee the potential implications of any changes they would make, right? I call that sort of the entire code base as a giant CSS file scenario, right? Where sort of nobody dares to reuse or change anything, and everybody just adds new cases. So in a way, the additional investment, so if you're making with Rust initially, you're saving further down the line, right? Simply by being able to maintain good productivity, as well, of course, through Rust efficiency and cost savings resulting out of that. So when evaluating whether or not to choose Rust, the main questions to answer are typically, what are your requirements regarding reliability? What are your plans and requirements also for long-term maintainability? And what scale are you building your systems for, right? And thus, like, how much money could Rust potentially save you in terms of hosting compared to other technologies? And then based on the answers to those questions, the final question is, are you willing to make that additional initial investment sort of for the slower ramp up with Rust? And in some cases, answering those questions will not result in a decision for us, obviously, right? But in many cases, it will, I think. Things like your core business system, sort of that implements the core of your product somehow, right? So if there you care about reliability, long-term maintainability and these things, maybe more than in other parts of the system, right? Like maybe on top of that, sort of you have an HTTP API or so, where you might value the flexibility of something like Rails or JavaScript or so, and your reliability requirements might also not be as strict, right? For in any financial system, you generally have little tolerance for bugs, obviously, right? And you need stability at all times, so Rust is a great choice there. Plus, sort of the faster you can trade, the more money you make in many cases. So like Rust performance sort of has direct financial value there as well. Anything that's high throughput and sort of must have high performance is an obvious use case, right? For example, think like you have some sort of like a gateway proxy in front of a number of microservices or so, sort of that has to be like super high throughput, it needs to be super fast, should have minimal overhead, needs to be stable, and so on. And you also don't want to have garbage collector spikes, right? Where sort of your entire service is very slow every now and then for a short period of time. And of course, like anything you're running at large scale, right, sort of you will see big savings both in terms of energy and money when switching to Rust, as we saw before. So once you have identified a use case, the question is, how do you start, right? How do you adopt Rust, and what are architectures and strategies that work? And the simplest scenario, of course, is you're starting something fresh, right? As we saw before, the ecosystem is mature enough to build complete web backends. One thing to keep in mind, though, is Rust isn't necessarily your friend when you don't really understand the domain yet and are still exploring, right? Like while technologies like Rails are awesome for exactly that stage, but then sort of show their shortcomings at later stages of a project when you need to maintain a growing code base, as we saw before, Rust is kind of the other way around, right? Like it's awesome for long-term maintenance and maintainability with growing teams, but not so great for getting to initial prototype fast while learning the domain and figuring out the architecture along the way, right? The strong type system and the ownership system sort of just aren't really made for that kind of explorative coding. The clearer your idea of the domain as well as the architecture you're going for are in the beginning of a project, sort of the better it is going to go with Rust. Another thing to keep in mind is there's no Rust on Rails, right? Like no full-featured batteries included framework just yet. And there will likely be one eventually, but it's to be seen what that will look like. All the foundational building blocks sort of exist, however, but you will be sort of assembling them sort of into your own custom-made framework along the way. A scenario where that's not really a concern, though, is when you're building individual microservices in Rust only, right? In these cases, sort of many of the things a full-featured macro framework would handle for you might not be relevant at all due to limited scope, right? And I'd say this is the typical adoption path for Rust in backend web development, where sort of you have a bunch of microservices and you rewrite one in Rust because that has specific requirements, right? And the nice thing sort of that adoption path is it allows you to evaluate Rust without making a huge commitment, right? It's a limited scope project, and if Rust does not work for your team, you likely haven't wasted like a lot of time and energy yet, right, when you find that out. If it succeeds, though, right, it can be the first step on an incremental adoption path, right, when sort of you rewrite the second microservice and so on. An even easier scenario in many cases is implementing native extensions in Rust, right? Assuming you have a Node, Ruby, Elixir, or whatever application where you just want to speed up some individual parts, right? And so you can just rewrite those parts in Rust. And that was previously kind of impossible for many teams as it required writing C code, which is, as we saw before, is like juggling chainsaws, and you shouldn't really do that. But now with Rust, it's a viable option, right? And like with microservices, sort of this can also be sort of a first step on an incremental adoption path as well. So now finally, I'd like to spend a brief moment and look at the future of Rust in web development. So as we saw before, you're getting a lot of value out of Rust. You get like unbeaten performance and efficiency, you get awesome reliability and stability, and you get great long-term maintainability, right? Still, that comes at the cost of a bit of a slow initial ramp-up, as we saw before, as there's just a bunch of things to learn before teams are able to move at full pace, right? So the goal of the ecosystem is to make that start a bit easier, right? So that the initial phase where you're not productive at all is shorter and productivity increases more gradually. And that will happen by a number of ways, right? First of all, the language itself evolving and becoming more approachable. Frameworks becoming more mature, sort of, and like continue to improve their APIs, as well as new patterns and frameworks taking shape sort of at higher abstraction levels, right? So that eventually there will likely be something like a Rust on Rails, and that will also make the entry easier for a bunch of people. And then also, like, there's obviously consultancies like Main Matter that enable teams to start from a decent level of productivity from the beginning instead of from the bottom with no idea really how to make the first steps even, and then sort of we can pull those teams up the rest of the hill to full productivity. So we believe there's clearly a bright future ahead for us, also for back-end web development, and we believe that Rust is the entrance into an era really of web development where we have access to a technology that allows us to reach new and higher levels of efficiency, stability, reliability, and maintainability without giving up on developer experience and productivity, right? And even with much improved long-term productivity compared to other solutions. And with that bright outlook into the future, I end. Thanks for having me. I'll be around. Talk to me later if you're excited about Rust. I don't know whether I can take questions, maybe? Yeah, please.
So you've talked a lot about using Rust on the backend. Have you investigated any kind of ideas for using Rust on the front end, compiled to web?
Yeah.
Okay, hey. So it was great talk, thanks. You've talked quite a lot about using Rust on the backend. Have you investigated or tried using also Rust on the front end with compiled to WASM type of scenarios?
Yeah. We haven't run Rust in the front end in the browser yet. I think it's interesting, but I think there are just very few use cases in reality. I mean, there's obviously Figma. I know there's a company in France that do what Figma does for design, they do it for architecture, right? So you can sort of do that in the browser as well. So, I mean, there are some use cases, but very few, right? So I don't believe it's really relevant. It might become more relevant in the future. I don't know, right? And also sort of a rewrite of something like React, whatever, would also not really make sense because it's so expensive sort of to call from WASM into like into the browser APIs and so on, right? So I don't think in the next few years it's going to be relevant. What we have done is we are running like a very simple edge function that we wrote in Rust, and then so if you can compile that to WebAssembly, and I think Netlify was so fastly everybody supports WebAssembly on edge functions. I think that's maybe a bit more relevant, at least for the next few years, and then sort of there's all these things where WebAssembly is used for plugin systems. I think even in embedded they use WASM now. So I think it turned out that WASM is awesome for many things, but not really, or like not mainly for the thing it was originally invented for. Any other questions? Good. Yeah, thanks for coming.